which is today because it's not really tomorrow.
All right, so we have a lot to talk about with the shape, but I've tried to boil it down for you because I didn't want you to have to write a million things, but I didn't want you to ask me like for the next 4 weeks why the shape is what it is. So I'm trying to balance out what to do here. But first I want to mention with the notes, when it says describing, that should be socks. But for us, we don't really have a way to establish outliers, so it's just going to be shape, center, and spread. Does that make sense to everybody? So I'm hoping by chapter 6, when you hear describing, you're going to think socks or doffs and everything socks except for scatter plots. Okay. All right. So for binomial, and this is what we did on Wednesday, the binom PDF and CDF. Binomials can be anything. Which is kind of annoying because you actually have to like figure it out. And that's what I wanted to work on today. But I have put 4 bullet points with some tips for you on how to determine the shape. And the first one, and my favorite, is to check a histogram. And I'm really going to point out, I'm going to do a shout out for number 93 in the homework. They really put you through creating a histogram there and then using that to determine the shape. Okay, but I want you to remember what you did. What did you do to create that histogram? You did a bunch of binom PDFs, correct? Is anyone engaged with the material here other than Ivan? Anyone else? Anyone else? Thank you. So you remember doing like a crap ton of binom PDFs. Okay, so that's one way. If you have the histogram, go for it. Next tip, check the probability model. If you have a probability model that's a table, you should be able to visualize the histogram in your mind without making it. Okay, so let me give you an example of what I'm talking about. If you flip back to the notes from, this is the notes from Wednesday, you can tell this bar would be 0.4, and this bar would be 0.4, and this bar would be 0.15, 0.02, and 0. And you could tell that the tail is over here, makes it right skewed. That's what I'm saying there. So if you have the table, then you can just visualize the histogram in your mind without making it. Don't you wish that they would have let you do that in number 93? Okay. Or here are some other strategies. Compare the mean and median. And we did this one the other day. And just remember, the mean will be pulled into the tail. So if you have the mean and median, you can say, oh, the mean is above the median. The mean will be in the tail, so it's right skewed. If you want to make yourself a little skew picture here, and the median should be somewhere here, but then the mean would be pulled into the tail. Why? Because it's not resistant to outliers. So all of those outliers go in the calculation of it. Okay, and the last one, which I'm going to affectionately call, yes, on my video, the Bryce Mincy method. Do you guys know Bryce Mincy? Do a few binom PDFs. So Bryce Mincy was smart enough to figure out how to do binom PDF in his L2, which created the probability model for him immediately. He just put it in the top of L2 and hit enter, and then it filled in all of the probabilities. I'm like, dang, I've been teaching stats for quite some time. That didn't even occur to me as an option, but I thought it was super cool. Anyway, we're going to practice this method, the Bryce Mincy method, down in our infected tree situation down here. Okay, now this is the bit, the large counts condition is going to go with us through the whole rest of the school year. But I need you guys to just put your pencils down. Just put your stuff away, not stuff away. Just put all of your distractors away for a moment and indulge me in this picture. This is a picture that I stole out of the CPM teacher's manual. And again, I don't love the CPM book for stats, but there are a few things I like, this being one of that. These are all binomial distributions. Okay. So, and they gave you the number of trials and the probability of success on each one. So the top ones have 10 trials, and then notice the probability of success increases as you go across. And the number of trials increases as you go down. Okay, does that make sense? 10 trials, 20 trials, 40 trials, 80 trials. So think like about 80 question multiple choice quiz. This one would have 10 answer choices each. You know what I mean? So 0.1 probability of being correct. Okay, now what I'd like you to do is examine those in your mind and just choose which ones you think look normal enough to use normal CDF. Just make a judgment call in your mind. Which ones do you think are okay to use normal CDF on? Then you would feel comfortable using normal CDF on. I'm hoping that you notice that the middle column is more normally, and the more trials gets more normal. So this is kind of like a limit situation again. So the closer you get to 50-50 and the more trials means more normal. Okay, what I've done, and I think like this region here looks pretty good. What do you guys think? Okay, is that what you came to too? Same conclusion? Okay, so what I did was I went ahead before school and I took all of the numbers of trials and the probability, and I calculated the projected successes and failures for each one. So what I mean is this number is the number of trials times the probability of getting it for of success. This number is the number of trials times the probability of failure. So this is if there's 40 trials in this one, 4 successes, 36 failures. 12 successes, 28 failures. 20. 28, you got what I'm saying here? Okay, the reason I wanted to put this, make sure this is on video so I can refer this back to you. I want you to notice that the ones that we like, these guys here in this region, all have successes and failures greater than or equal to 10. This is the rule for stats that the whole world has decided on. 10 is the lowest that they're willing to go for successes and failures to be able to use normal CPF. And we're not going to sit and talk about why for the rest of the year. You're just going to know it in your head from using it a bunch of times. You're going to say success is greater than or equal to 10, failure is greater than or equal to 10. And if you don't know why, come back to this picture and be like, oh, if the successes is less than that, then my graph is too skewed on one side, meaning that there's a tail. Do you know what I'm saying? Okay, so this video will always be here for you. You know, we'll always have it. We can look back on those. But before we put these numbers up, we agreed this was kind of our good zone right here. And the cutoff is 10. There's a full algebra explanation of this that I could do for you that I'm not going to do because College Board will never ask. They're just going to expect you to be able to use this. But I just wanted to put the calculations up for you. Okay, so we're just going to summarize it back in our notebook. I just didn't want to put you through all of that. Okay. First thing we're going to say is N equals number of trials. P equals probability of success, remembering that a lot of times success is not a good thing in these, including infected trees, which is kind of sad. Okay, now there is part of this is kind of dumb because why would you want to use normal CDF if you have binome CDF and CDF and those things? Why do you need to use normal CDF? And I think it's because like a lot of the research world wants to put everything into a normal curve. They just want to force it to be a normal curve. So everyone's like, it's the bell curve, you know? And so I feel like there are instances when that is kind of all the research community does. But you guys, after taking this class, I hope that you'll walk out knowing that there's a lot of other types of shapes of graphs other than just the bell shape. That it could be skewed, it could be uniform, it could be really, really wonky. Don't just make the assumption that everything is normal in research because it's not. But I get why they would want to force it to be that for simplicity's sake. Okay. So you guys wrote this, correct? Okay, that's the last thing you wrote? Okay. Does the infected tree situation satisfy the large counts condition? If not, predict its shape. Okay. Do you remember what the number of trials was from the infected trees? The very, very first one we did? 30. Great. And what was the probability of success? Yep, beautiful. Okay, so what we're going to do is large counts condition, super easy. We're just going to plug it into these two things and see if they're true. That's all we have to do. And then sort of picture what it would be in our mind. So 30 times 0.16 greater than or equal to 10. And when you write that, say, like, put a little inflection in your mind, like, is it? You know? And then 30 times prep, already screwed up. Are you watching me struggle over here? Okay, and I know 3 times 16 is 48. So this is 4.8 greater than or equal to 10. Nope. And this is 25.2 greater than or equal to 10. That one's correct. Will it work for us if it's just one and not the other? No, it has to be both. Also, real quick note, these are, for lack of a better word, complements, not the right word, but this is everything else. So you don't really have to calculate this in your calculator. You could just do 30 minus 4.8 because this is successes, this is failures. So once you find this one, you could just subtract this from the total. Or you can show the work and do it. Anyway. Okay, so we have sad news. It's not normal, which means that we need to do more work. And this is where we're going to do the Bryce-Mincy method. So if you guys could grab your calculator. And we're not going to do the full L1 situation. Bless his heart, he is too smart for me. He's just one of my stat students from last year. Yeah, and he's one of those people who would just sit and mess around on the calculator and like figure stuff out because he liked to. Like it was just really cool. Anyway, okay. So we're gonna do the method where we do a few binome PDFs. So go over here make yourself a little, we're gonna just do a little baby histogram. We're not even gonna do the whole thing. We don't need to. Oh goodness, look, it's already there. It's like I was practicing this before you came or something. Okay, so that's like basically nothing. Slightly more than nothing. 3%. Ooh, 8%. Mm. Okay, now I should have drawn this differently, but I need you guys to understand this does not, this goes out to 30. We're not going to do them all. We're just going to go until 56. Okay. Do you guys see that it's starting to come back down? Also, do you see that I've taken up almost all of the 100% already? Because all of the bars have to add 100%. Okay, do you notice that 4 and 5 are really closer to this side than 30 would be? So 30 would be like over here. That's gonna be like a super long tail. So right skewed. You can tell it's right skewed because it peaked much closer to 0 than it would be to 30. 30 would be way over there. So it started peaking right away. So you're like, ah, right skewed. I don't need to do any more of the graph. It was just like last night in your table when you guys, did you guys get scientific notation underneath your do you guys know what I'm talking about? Okay, that just basically means that there's a teeny tiny number and it's basically 0 for our purposes. Okay, so I just said, I made myself a little note, right skewed because the mode is much closer to 0 than it is to 30. Yeah, the peak of my graph, basically. And you don't even need to make a graph. You could just keep hitting enter and like just analyzing the numbers. Okay, now after you write this stuff down, it would be great if you could grab your yellow sheets. We're gonna write some stuff just a little bit in our yellow sheets. I don't know where mine is. Oh, it's right here. Okay, so your yellow sheet has an entire box for chapter 6, which is super cool. And I'm gonna label it. You guys are allowed to label it chapter 6. You can use this entire box. You don't need to put that on your note card. You can use your yellow sheet. Here's your expected value. This is top times the bottom plus top times the bottom plus top times the bottom plus top times the bottom. And then there's how to get the standard deviation. If you have the table, we did it by hand. I don't know if you remember 6.1a. Okay, this is the box we're in right now. Binomial distribution with parameters n and p. There, they gave you the binomial formula. Look how nice they are. They gave you the pre-calc notation there. And here is your mean. Okay, however, I want to add one more thing to this. I want to add this. Remember that mean and expected value are equal. They say it up here, but I want to make sure that you put it in here. And this is going to be what we do on Thursday of next week. But why not? I just want to remind you that we use the words expected value and mean interchangeably, and those are exactly the same thing. Okay, but here's your formula for what we're doing in this problem. So the mean of x is n times p. So mean of x is n times p, which is great. Do you know why? We already did it. We did it in the large counts condition here. So the mean is just the number of successes. Okay, interpretation. If many trees are randomly selected, the mean number of infected trees is 4.8. And when you're doing the binomial stuff, you need to add a little bit and say how many that you actually looked at. Any questions about the sentence? Good. Okay. Now go back to your yellow sheet and find the standard deviation formula for binomial. Do you guys see it in your yellow sheet? Make sure you see it. Okay. Don't know why. You're supposed to say hi back. I just wanted you to know that you didn't ninja me this time. And there's those words you're really looking for. You typically see the word typically in the standard deviation interpretation set. Mhm.
Why do you use mean and not mean?
I don't know. But we did find the median earlier. So if you, I don't know if you remember, but the way to find the median is to do a cumulative probability table and find the first time that it hits 0.5, and that will be your median. But I feel like the research community asks way more about mean and standard deviation than they do about median and IQR. And if I read reports of data, I very rarely read median and IQR, and I almost always read mean and standard deviation, even if it's not appropriate. I feel like median is more appropriate when it's skewed. So, but if you're asked to find the mean, you can't. Now, along with what Jeremy was saying, though, what was the median of this problem? Did we find it? So we could do Bynum CDFs of this until we got to 0.5, right? Which I'm pretty sure would be less than 4.8. So you could compare the mean and median to find your shape then. Anyway, is everybody done with the writing? I'm gonna flip my page over. Yes? Okay. So as of today, there are 1,372 students at BHS. So when you're writing this, you have to visualize 1,372 slips of paper and a half. Fun.
Yeah.
Okay, so while you're finishing this up, we'll talk about what this means. Some of the questions that we do in the stats book are not about research as far as like measurement. The infected trees one was like a research thing. Sometimes though, we use random sampling. Okay. And you take like people's answers to a survey or something, and those can be binomial. Except the problem is with independence. And so sometimes, and even the trees condition, if you think about it, because if you take one of the trees and that tree's not open to you to be the next one to choose, technically that's sort of violating independence. So, there is a clause in stats that lets us bypass the independence condition a lot of times. And it's called the 10% condition. And so we're just gonna spend a second on it because it'll make it able for you to use binom, PDF, and CDF, in other situations, which is great. What I want you to do is indulge me here. Okay, and I want you to imagine all of the 1,327 enrolled students at BHS's name, it's in a hat. And I want you to think about what's the probability that I draw out Cameron. That would be 1/. Okay, and then Cameron's out, she got picked. What's the probability that I draw out Ivan? Right, okay. And then Cameron and Ivan are in. What's the probability I draw out Jackson? Okay, what I want to do is show you that these are just really not that far apart from each other. So that's kind of the thing. This is 7.5 times 10 to the negative 4, which is 0.00075. And this is, if you round it, 0.00075. And this is, just take a wild stab, 0.00075. Okay, now does it make sense to you though that as more names get picked up out of the hat, these fractions will get farther apart from each other? There's a much bigger difference between like 1/2 and 1/3. So the line is, what's the line? Like, where is it okay? Where can you assume that these are the same? And it's 10%. So if your sample size is less than 10% of your population. You can say the situation is independent. Even without replacement. So you're sort of cheating, except how different are the numbers really? Not that different. Okay, but now we have a situation. This is the last example. It has some parts to it though, so don't get excited. This is the last example we're gonna do today. And the first thing we're gonna do is notice that it's a survey. Surveys are inherently without replacement because you're not gonna ask somebody to fill it out twice, if that doesn't even make any sense. So what we're gonna do is use our new rule to satisfy the independence condition, because this really isn't independent. Okay. Do you guys remember the 4 requirements for being a binomial? And let's not do independence first. Let's do independence last. Success or failure. Okay. Is this a success or failure situation? Yeah, they own a debit card or they don't. Okay. Is there a consistent probability? I kind of gave you some stats overlord knowledge in this problem, meaning that you wouldn't really know this if you were doing the survey. But suppose that exactly 12% own a debit card. Yes. Is there a fixed number of trials? Okay, the only question here really is it independent? And so what we ask ourselves is our sample size less than 10% of our population? The population is teens. Is 500 less than 10% of all teens? Okay, so what does that mean I get to do now? What does this allow me to use on the calculator? Yeah. Okay. I love you all. I need you to write like the wind Bullseye. Do you know who Bullseye is? Do you know how fast he runs? Like the wind. Okay, I'm gonna need you to write like the wind. Are you prepared? Okay. I know that guy's probably not gonna write like the wind, but you could. That's a really good question. I don't know that he has a pencil. He seems to be pencil free. Okay, I have a whopping 7 minutes to finish teaching this. I can do it though, because I'm a caffeinated lady. Okay. Estimate the probability that 50 or fewer teens in the sample have a debit card. Question number 1. Can I use the binomial distribution for this? Let me ask again. 4 check marks. Can I use the binomial? Okay, 50 or fewer. What alligator is that? 50 or fewer. Less than or equal to. Nice. Okay. And that is regular binom CDF without any of the hijinks that complements and things. Okay, number of trials, 500. Probability, 0.12. 50 or fewer out of the 500. Are you guys okay if I write down the number that I got before you got here? And you know where to find this and where all those numbers came from. Okay. Justify why X can be approximated by the normal distribution. This is the thing that we learned at the very beginning of the lesson today. So you have to have N times P is greater than or equal to 10. And N times 1 minus P is greater than or equal to 10. Do you guys remember all the pictures I showed you with the successes and failures on it? And the zone we liked was all greater than or equal to 10 for both numbers. Okay, in this problem, N is 500, which is a lot of trials, which is good. P is 0.12, which is kind of one-sided. But it worked. And you know why it worked? Because 500 trials is so big. The really probability isn't going to matter that much. Okay, last thing. Verify your answer from B, but now it says use the normal distribution. So we're going to do normal CDF. Okay, now here's my question. If it's less than or equal to, what is the low? Negative infinity, beautiful. What is the high? What is the mean? It's on your yellow sheets, and we're going to write it in here as a calculation. So, yep, it's 60. Great job. So N times P, comma. Did you know that you could type calculations into normal CDF? You can. What is the standard deviation? That other thing? Nope, it's the one with the square root. Do you remember from the yellow sheets? I don't know why I put an extra comma. There should not be an extra comma. I don't know what happened. Okay. Are those two exactly the same? 0.093 and 0.084? No. And here's the really, really ugly news. The binomial one is more accurate. Because we had to do a bunch of rounding and estimating to get that guy. Why did we go through the whole process then of saying that it was normal and using normal CDF? Because, as I said, the rest of the world forces everything to be a normal curve. So they don't know about stat like we. Yeah. Duh. I did it. This is Talbot, you did it.